Okay, welcome back. This is Mr. Hassan's Maths channel, and I'm now answering question number 7 from the International A-Level Edexcel Mechanics M1 June 2021 exam. I'm now, as I said, on question 7, a non-uniform rod AB. So this is a rod that's non-uniform. The word non-uniform is very, very important in this question, okay, in these type of questions. The word non-uniform basically is telling us that this rod, its center of mass, the place which we take the weight to act through, is not in the geometric center. It's not exactly halfway along the beam. Okay, so that's very important. So we know from the wording that it's non-uniform, we can't assume that the weight acts in the center of the beam or through the center of the beam. Whereas if it was a uniform beam, we know that the weight, we can take the weight is acting through a point in the center of the beam, the center of mass. Okay, so a non-uniform beam of mass AB of mass 60 kilograms and length 8 meters rests in equilibrium in a horizontal position on two vertical supports. Okay, one support is at C, where AC is A, and the other one is at D, where DB is 2A meters, as shown in figure 2. The magnitude of the normal reaction between the beam and the support at D is 3 times the magnitude of the reaction, of the normal reaction between the beam and the support at C. So when there's two surfaces in contact, there's always a reaction force between them. Okay, so there's a reaction force of the beam of the support on the beam, and there's also a reaction force of the beam on the support. Now, by modeling the beam as a non-uniform rod whose center of mass is at a distance x meters from A, find an expression for x in terms of A. Okay, so let's take that information. We have a mass of 60 kilograms acting at x centimeters from A. Okay, so let's just say that the x centimeters is, let's make this small, x centimeters from A, sorry, x meters from A, not centimeters. So let's just say it's over, let's just say it's over here. It says the support, it says that the, what did it say? The reaction at D is 3 times the reaction at C. So we can assume that it's going to be closer to D, although it really doesn't matter if you don't realize that it's going to be, as long as you draw it between C and D somewhere, you'll be fine. Okay, it's an equilibrium. Okay, but it's definitely going to be closer to D. You don't have to draw it in, but your maths at the end will show you that it is closer to D. Okay, because there's a more force on D than C because the reaction at D is greater. Okay, so that's the center of mass. We assume that it's acting at this distance x. They've told us it's x meters from A, the center. So the weight of the beam is 60 kilograms. So that's 60 newtons. That's mg. 60 g newtons. Sorry, 60 g newtons. Okay, so it's 60 times 9.8 newtons. I'll write it as 60 g. That's the weight of the beam. The mass is 60 kilograms. The weight is 60 g. W is mg. Okay, the weight is mass times g. Now, then it says one support is at C. Okay, so the magnitude of the reaction at D is 3 times the magnitude of the reaction at A. So there's a reaction force at D, and there's a reaction force at C, support at C, where the supports are, D and C. And the reaction at D, let's call it 3R, because it's 3 times the reaction at C, which is, we're going to call it R. That's 3 times that. Okay, now, important point is some students say, what about the reaction of the beam on the support? Well, we are considering here the forces that are acting only on the beam. We are considering just the beam alone. We're not considering anything else. So we're considering the forces acting on the beam. Yes, there is a force acting on the support from the beam, but we're only looking at the forces that are acting on the beam. That's what we're looking at right now. Forces on the beam. Okay, so that's why we don't put another reaction force here. If we were looking at the forces acting on the support, there would be a force acting downwards on the support from the beam. Okay, but we don't consider that here because we're looking at the forces that are on the beam, which are its weight, and these two reaction forces from the supports that it is resting on. Okay, so we got to find an expression in terms of, for x in terms of a. So first of all, we are able to find the value of R because we have the reaction force and the reaction force in terms of the same letter R. Okay, because this is 3 times that. So if I resolve my forces vertically, I can say that R plus 3R is equal to 60G, the weight of the beam. Okay, there's nothing else that's being placed on this. It's just the weight of the beam. It's just a beam resting on the supports. There's no other weight or anyone standing on it or anything. So we can just say R plus 3R is equal to 60 G newtons. So 4R is equal to 60 G. So therefore R is equal to 60 over 4, which is 15. 15 times 4 is 60. So R is equal to 15 G newtons. So that we can now say, I can now say that this is 15G and this is 45G. Okay, so I now know the values of the reaction forces on the 2 supports on the beam, acting on the beam. Okay, so now what we can do now is to find x, we can take moments about wherever we want. Now, as we want to find the distance of the center of mass x from A, it says x meters from A, the most sensible thing to do would be to take moments about A. Okay, about the point A. I mean, we could take moments about C or D, okay, and that would eliminate one of these forces, but we don't really need to eliminate one of these forces because we know what both of them are. If we didn't know what one of the forces were, then yes, we could take the moments about C or D, the one that we didn't know, and that would eliminate the unknown from the equation, and then we could carry on. But here we know the both forces, and instead of in the end adjusting your answers, especially here in terms of A's and stuff like that, it's, I think, more sensible for us to just take moments about A. That's what I would personally do. So if I take moments about A, I've got to think about the distances of everything from A. Now, the first support is distances A from the point A meters from A, small a from A, and the weight is x meters from A, and the other support is this distance away from A here. Let me just use another color, another type of arrow. So the distance from there to there, which is the distance of the other force from the support, the reaction force, that is basically 8A minus 2A, which is 6A. The whole thing is 8A, that's 2A, that's 6A. So if we take moments about A, we can say that the clockwise moments and the anti-clockwise moments are equal because it's in equilibrium. It's at rest in equilibrium, horizontal at rest in equilibrium. So we can say 60G times x, that's the clockwise moments, is equal to the anti-clockwise moments. If we take an A as the pivot, that would be anti-clockwise and that would be anti-clockwise. It would cause that type of rotation about A, if we could do that. So that's 15 times A. And over here you have 15G times A. Be very careful about the G. That's 15G times A. And then you've got 6, that's 45G plus 45G times 6A. Okay, so this is the force and this is the distance. That's the moment of these forces about A. Okay, so the clockwise moment is 60G times X. The anti-clockwise moments are made of 15G times A and 45G times 6A. So when we calculate that, the G's will cancel out because it's in every single term. So we've got 60X equals 15A plus 6 times 45, that's 240 plus 30, that's 270A. So we can say that 60x is equal to 285A. So x is equal to 285 over 60A. Okay, so let's see, 5 goes into, let's just put it in the calculator, no problem with that. 285 divided by 60. That gives us 19.4, which is 4.75. 4.75A. Remember, there's an A with this, meters. So x is equal to 4.75A meters, and there's the answer to part A of this question. Okay, now for part B, it says a box of mass m kilograms is placed on the beam at E, where AE equals 2A meters. Okay, so it's now placed at E, which is somewhere which is around here. So there's a box that's placed here. Okay, this is a box of mass m kilograms. So you're going to have its weight acting down here of m kilograms. Okay, so that's m kilograms. So it's mg newtons is its weight. And its distance is basically that same distance. Okay, it's 2a. So it's like 2a away from the side A. So AE, this is the point E. Okay, I'll call it E. And that is 2a meters. All right. Then it says the beam remains in equilibrium and in a horizontal position. The magnitude of the normal reaction between the beam and the support at C is now equal to the magnitude of the normal reaction between the beam and the support at D. Okay, so now we know that these two supports have got the same. These two supports are both equal to the same amount. Okay, the reaction forces are equal. So if this is R, this is also R. They both are. They're both the same now. Okay, so it says by modeling the box as a particle, find the value of M. What it means by modeling as a particle, it means that assume the center of mass is acting like through a point. It's just like you take it as a point, not like spread over a little area. So like we've done here. So now we need to find the value of M. Okay, we need to find the value of M. So let's see how we could do this now. What we could do is we could set up an equation if we again resolve forces upwards, but we'll have two unknowns this time because we'll have R plus R, which is 2R, equals mg plus 60g. Okay, so we have one equation here which has got two unknowns, which is m and r. Okay, and then we can also take moments about, again, any point that we want. Okay, we could take it about A again. We could take it about R if we wanted to. This C if we wanted to. We could take about D. But what we could do here is if we take the moments about E, okay, we can find out what R is. And once we find what R is, we can find what M is. That's one strategy. Okay, there's probably lots of different strategies that will work. Like if I took moments about A, for example, I will have an equation with R in it and M in it, and I can solve these two equations simultaneously. I could do that way. Or I could find what R is by taking moments about E. That way I can ignore the moment mg because the distance from mg from E would be 0. So there's two different strategies I can think of doing. Let me try the one that might seem maybe it's a bit easier because you don't have to deal with simultaneous equations there. You just find what R is and then you can find what M is by substituting into here. So it's like a bit more, I don't know, seems a bit more sensible to me, but let's see what happens. So let's take moments about E. Let's take moments about the point E. If we take moments about the point E, then the clockwise moments about E would be the weight. Okay, so now you got to just do a bit of adjusting for the lengths. Okay, because if that's 4.7a and that's 2a, this must be 4.75 minus 2, which is 2.75a, the distance from E to the weight. So we could say that that's 60g times the distance, which is 2.75a. That's the clockwise moments acting here. Okay, of course, the weight of the box is acting right through E, so it doesn't have any turning effect. So that's why we took it there, so we could ignore it. And that's the clockwise. And also the clockwise moment actually would be this as well, because if this is the pivot, it would like tilt like this. So this is also a clockwise moment, this R. So we've got to find out this distance from here to here. And well, we know that's A because this is 2A. So this is A. So we can say this is going to be R, which we don't know, times A. So those are the clockwise moments, these two. And this would be the anti-clockwise moment, the one up here, because if this is the pivot, that would cause a rotation like that. If this is the pivot, this causes a rotation like this. If this is the pivot, it causes a rotation like this. So these two both are clockwise, and this is anti-clockwise. So this one is going to be anti-clockwise. So that's going to be the distance between E and this point here. Well, from here to here is 8. From here to here is 2A. So from E to here must be 6A meters, because this from A to E is 2A. Okay, so from here to here is 2A. Okay, and this is, sorry, from there to there that's another 2A here. It's not 6A actually. All right, because from here to here is 2A. from here to here is also 2a. So this is actually 4a. The distance from the point D to the point E is 4a meters. Okay, because there's from this point to this point is 2a. From this point to this point is also 2a. So what's left? 4a meters. Okay, so you got to be careful about that. So that's equal to r times 4a. Okay, so now this is an equation which the only unknown is the r, because the answers are going to be in the end in terms of, well, the a's will actually cancel out from every term anyway, because you've got a and a and a. Okay, so you'll end up with something in terms of just r. So this gives us 2.75 times 60g. Okay, so you have 2.75 times 60. I'll leave it in terms of g for now. That gives you 165g times a plus a times r equals 4a times r. Okay, so if we bring, well, the a's cancel out. So if we bring the r's together, this is 3r is equal to 165g. Okay, and so therefore we can say r is equal to 165 divided by 3, which gives us 55g. So r is equal to 55g. Now, if we know r is equal to 55g, then we can use equation 1. We can say r equals 55g. Put that into equation number 1. So we have 2 times 55g equals mg plus 60g. So we can find what m is now. So we have 110g minus 60g equals mg. Okay, you can see the g's will cancel out. 110 minus 60 is 50. 50 plus 60 is 110 equals m. So m is equal to 50 kilograms. And there's the answer for part B. And I think that was the end of the question. Yeah, that was it. That was the last part asked. So there we have the answer to question number 7. As I said, there's different ways you could have gone about doing this. You could have set up an equation from this as we did, and then we could have set another equation which has both m and has r in it by taking moments about a, for example. And you would have ended up with a pair of simultaneous equations which you'd solve and get the same answer. Okay, so there's different methods or different approaches you could take. I decided to take moments about E because I see that that will get rid of the M and I can find what R is. And then as I did, substitute that R into this equation to find what M is, which was the goal. Okay, so there's the end of question number 7. Other questions about this topic of statics and moments you can find in this is like moments really. You can find in the playlist that should appear over here somewhere. Above that will be the playlist which should contain all the questions from this past paper, June 2021 M1. You can subscribe to my channel over here. And if you want to see the other papers I've done, other types of papers like the P1, P2, P3, S1, and the IGCSE papers I've done, you can look at the index, which is found in the description below the video. Thank you for watching and see you soon.